Boys and girls, notice that the name of today's lesson has to do with rational and irrational roots of polynomial equations. And before we start talking about that, let's go back and review our number system a little bit, if we can. And if you remember, one of the first set of numbers that we ever considered was that set N, which we call the set of natural numbers. And if we were to list a few of these elements, let's indicate what that set of numbers is going to be, and we can start out by saying what? 1, 2, 3, and so on, indicating that this is an infinite set. From our set of natural numbers, we then went on and talked about that set which we call J, and does anyone remember the name of this set of numbers? And we call this, Tim, the set of integers. And if we were to list a few of those elements, one pattern that we used was to indicate the element 0, and then 1, negative 1, 2, negative 2, and you see the pattern, and so on forever, okay? And then we made another jump to another set of numbers which we called F, and does anyone remember the name that we gave that set of numbers, Brenda?
Rational.
That was the set of rational numbers. We used the letter F because of the fact that we have for the first time a field, is that right? And we can't very well indicate those numbers in terms of a list, but there's a pattern that I think we can write. Let's write in the pattern of P over Q, all right, where now P can belong to the set J, and Q then is going to belong to what set of numbers? Rather than calling it the set J, let's exclude 0, and let's decide to call it, Steve, natural over the set N of natural numbers. And then from here, we then made a big jump, if you remember, by having the completeness axiom. And then finally, we had that set which we called R, which is called the set of what? The set of real numbers. Okay. Now, from our number system, what I'd like to do is to look at perhaps another kind of a number. Let's call this idea 1. And then suppose, for example, let me pick out some small set, 2, 5 thirds, or let's see now, negative 17 twelfths. And here we happen to have three elements in this set, and certainly it is a subset of what set of numbers as we have indicated here. And the smallest such subset would be what set of numbers that we see here? Brenda?
Rational.
The set of rational numbers. Certainly it would be over the set of real numbers, but this is these three elements, this little finite set, would be a subset of the set F. Is that right? Suppose I then were to write another set. Suppose I were to write the square root of 2, the cube root of 17, the fourth root of 5, and here we have a little set, and certainly this is not a subset of the set F. Is that right? I think we'll all agree that it's not a subset of the set F. Now, the question is, if we were to look at these elements, root 2 and the cube root of 17 and the fourth root of 5, this certainly is over the set of real numbers. They are real numbers. It is a subset of the set of real numbers. But the question is there some other kind of set of numbers which is not rational but still real? And what name have we given that set, Doug?
Irrational.
That's what we would call a set of irrational numbers. Let me just indicate that by writing out that phrase, the irrational numbers. If we were to call the set of rational numbers F, let's use the notation of not F to indicate the set of irrational numbers, all right? So that if we then were to take the set F, union not F, what then is the union of F and not F equal to? What would you like to say that this is equal to, Bill?
The real number.
This is over the set of real numbers, all right? So the union of the rational numbers and the irrational numbers is certainly then going to give us the set of real numbers, okay? Well, let's see, I think there is another idea that we can look at. Suppose we were to take, let's take one of these irrational numbers, such as the square root of 2, and to it, let's add a rational number, such as 3. And if we were to add these two numbers, the question is, what kind of a number do we end up with? And, well, we certainly cannot indicate, we cannot add these two. All we can do is to indicate this sum, and what kind of a number then is root 2 plus 3? And this would then belong to what set of numbers, Tim?
Irrational numbers.
The set of irrational numbers, and using our notation, this is certainly F prime. All right, it then would belong to the set of F prime. Suppose we were to take the difference between an irrational and a rational number. What then can we say about this difference? What kind of a number is this, Bill?
It's also an irrational.
It's also an irrational number. Suppose we were to take an irrational number and multiply it by a rational number. In this case, if we were to indicate this multiplication, I think you will agree that this is also an irrational number. And finally, well, let's take, say, the square root of 2 divided by 3. And what kind of a number is this? But it is also, Tim,
Irrational.
an irrational number, which we can indicate as f prime. Now, let's then go on and look at a fourth idea. Suppose we were to take, say, the square root of 2 and add to it the square root of 3. Now, by this sum, the question is this rational or is it irrational? And I think from what we have seen thus far, you would have to say that this belongs to what set of numbers? This belongs to, Tim?
Irrational
The
number.
set of irrational numbers. Is that right? Now, don't be fooled, however, by taking, notice in the first case under 3 here, the sum of any irrational number and a rational number. The sum and the difference and the product and the quotient of an irrational number and a rational number is always irrational. And I think one might be led into the trap, so to speak, of saying that therefore certainly if that would hold true for an irrational and irrational, certainly the same thing would hold true for an irrational and another irrational. We should end up with an irrational. Now, let me see if we can't find an example. Suppose I were to add to root 2, let me add the negative of root 2. And now root 2 plus a negative root 2 is what kind of number? That's equal to, of course, equal to, John, is 0. And 0 is what kind of a number? 0 is,
Integer.
it's an integer, and therefore it certainly is what? It certainly is rational. So here's a case where this belongs to f, okay? Similarly, well, if we were to take root 2 minus a root 2, this certainly is a rational number. If we were to take, say, root 2 times root 2, here now we have the product of two irrational numbers, which in this case is what? This is 2, which is certainly a rational number. And if we were to take the square root of 2 divided by the square root of 2, we know that this is equal to 1, and therefore it belongs to what set of numbers? A rational number. So in this case, the sum of two irrational numbers, the sum and the difference and the product and the quotient, is not necessarily an irrational number, and it can be a rational number, as we can see here. So in other words, the irrational numbers are not closed with respect to our operations. Okay? Well, all of this is a little bit of background material to build up to another idea, which is really the name of today's lesson. And let's see if we can't pursue that idea right now. Suppose we were to look at an equation, 15x squared minus 2x minus 8 is equal to 0. Here we have what we may think of as a polynomial equation. In fact, we may call this a polynomial equation in simple form. We have a polynomial in this case is equal to 0. Now, looking at this, the only way that we know how to solve this, if it is solvable over the set of real numbers, is to try to factor it. And so we look at it and we say, well, let's see now. I have probably a number of choices. Let's try 5x times 3x is 15x squared. And now let's try to find two numbers here whose product is negative 8 and whose sum is a negative 2x. And can anyone come up with some numbers here which might do this? And Peter?
Plus 2, 5x plus 2.
A 5x plus 2. If we then had a 2, that would then give us a 6x and a 20x, and I don't think we can get a 2 out of it that way. Doug? Let's see. Steve?
5x minus 4.
A 5x minus 4
And 3x plus 2.
and a 3x plus 2, I think is perhaps what Peter had in mind, because there we have a negative 12x and a plus 10x is a negative 2x, is that right? And a negative 4 times a positive 2 is a negative 8, and sure enough we have factored it. Now looking at this, our theorem tells us then, one of our theorems tells us that therefore this product of this factor is equal to 0, or this factor is equal to 0, and therefore we have x is equal to 4/5, or x then is equal to a negative 2/3, and we say that our solution set then indeed consists of both of these elements, and if we were to check, I think you would agree that our solution set would be 4/5 comma negative 2/3. Now, there's a very important theorem which I would like to introduce. And now let's look at these numbers that we have here as the roots, and let's look at the original equation and see if there's some pattern here that we can determine. Now notice that the number 4 is a factor of negative 8, certainly, and the number 5 in the denominator is a factor of 15. Also, notice here, let's take this dash symbol and think of it as negative 2 is a factor of negative 8, and also 3 is a factor of our leading coefficient here of 15. All right? So what the theorem says is that if x is a number in the pattern of p over q, where x is now a rational number written in lowest terms, okay, then what we can say is that p must belong to that set of elements which will be factors of the constant term here, which in the cases we have here, it can then be, let me write this as plus or minus 1 or positive 1 and negative 1. Let me use that notation. It's certainly a factor of negative 8. Positive and a negative 2 is a factor of 8. Negative 8. Positive and negative, what would be the next one? A 4. And a positive and a negative 8 would be the factors of negative 8. And then q would have to belong to what set of elements? Well, let's look then at the number 15, and all the possible factors of 15 are what? We can write what? Positive or negative 1, positive or negative 3, positive or negative 5, and positive or negative 15. And now, out of all possible numbers, out of all possible roots over the set of real numbers, if there are any roots that are rational, that is of the pattern p over q, where p and q are in lowest terms, then in fact what the theorem says is that they must be numbers which will be factors in the case of the numerator p of the constant term and the denominator q of the leading coefficient. All right? So out of all possible numbers, there are really quite a few finite ones that one needs to check. And in fact, if you look here, a positive 4 divided by a positive 5 would give us one of them, and a negative 2, say, divided by a positive 3 would give us the other one. All right? And this is really quite a powerful theorem to help us as we find some of our solutions to equations. Let's look at another example. In this case, suppose we had 5x cubed plus 18x squared plus 7x minus 6 is equal to 0. Okay? Now again, notice it's a polynomial equation written in simple form, in that we have a polynomial on the left is equal to 0. Our leading coefficient is 5, and our constant term is negative 6. So if indeed x is any number of the pattern p over q, that is, if there is a rational root for this equation, then it's got to be such that p must belong to what set of elements? Well, all possible factors of negative 6, which are what? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and, let's see, q must be a factor of what numbers? It must belong to what set of elements? Plus or minus 1 and plus or minus 5. Well, there are not too many to check there. Okay? Now, let's start out and actually search. Let's, out of all infinite numbers of possibilities, we've reduced it to a finite set. A rather large one, but still finite. Okay? So let's let q, say, be equal to the number 1. Let's hold q at positive 1, and let's check for all other possible values for p. All right, so if p, say, is positive 1, then, now let's actually just substitute in the original equation. Here we have 1 plus 18. I'm sorry, here we have 5 times 1 cubed, which is what? 5. It's 5 plus 18 plus 7 minus 6, and certainly that is not 0. Is that right? So 1 over 1 will not make the statement true. Now, if p then is, say, negative 1, let's see what happens. Here we have negative 1 cubed times 5. There's a negative 5 plus 18. Is that right? Minus 7 minus 6. And lo and behold, what does this add up to? There's a negative 13 minus 5 is a negative 18 plus 18 is equal to 0. Therefore, we have found a rational root. If there is a rational root, it's got to be of this pattern. It's of the pattern 1 over negative 1, which we call the number what? Negative 1. So we found one of these. Now, what we can do is to continue this search pattern and go through all of the other possibilities. But I think at this stage, I think there's an easier way out. And let's see what we can say. If you remember, well, let's come back, for example, right to here. If x is equal to 4/5, then 5x minus 4 is a factor of the original polynomial expression on the left-hand side. Is that right? So let's then use that idea over here. Therefore, what can we say but that x plus 1 must be a factor of the original polynomial expression on the left-hand side times some other factor, which we don't yet know, is equal to 0. Is that right? Now, how can we find this other factor? How can we find it? By division. So let's then actually perform that division. There's x plus 1 into, and what now here is going to be our divisor? What's going to be our divisor but the, what? The original polynomial on the left-hand side. Is that right? Which is what? There's a 5x cubed plus 18x squared plus 7x minus 6. And let's actually perform this division. X into a 5x cubed goes 5x squared. There's a 5x cubed plus a 5x squared. When we subtract, check my arithmetic, please. When we subtract, we have what? 13x squared plus 7x. That's a plus 13x. That's a 13x squared plus a 13x, which when we subtract is a negative 6x minus 6, which is a negative 6 times x is a negative 6x minus 6. And sure enough, a remainder of 0. Therefore, what is our other factor? Right here, we may write it in, and indeed it's right here, namely what? There's 5x squared plus 13x minus 6. This is a quadratic, and possibly, if there are any other rational roots, we can find them by factoring this quadratic. Let me repeat this line over here. Therefore, we have x plus 1 times, and there we had a 5x squared plus 13x minus 6 is equal to 0. And now let's look at that and see if in fact we cannot factor it. And you say, well, the only possibility is 5x times x is a 5x squared. And let's see, does anyone see anything, Peter?
5x minus 2
5x minus 2
is x plus 3.
times an x plus 3. There's a 15x minus 2x is a plus 13x and a minus 6. Does everyone agree with that? Therefore, using our theorem, a times b times c is equal to 0. Therefore, a is 0 or b is 0 or c is 0. Therefore, here we have x is negative 1 or x is 2/5 or x is negative 3. If indeed you were to substitute each number into the original equation, I think you would find out that all three numbers will make the sentence true, so that's our solution set. Again, notice that, say, you're looking at 2/5. Is other pattern p over q, where 2 then is a factor of negative 6, and 5, the denominator number, is going to be a factor of 5, okay? And similarly, negative 1 and negative 3 will also satisfy that theorem. Well, in fact, this gives us a method of looking at another type of situation. Suppose we had the equation x squared minus 2 is equal to 0. Now, if there are any rational roots of the pattern p over q, then the theorem that we have just developed says that p must belong to the set of elements consisting of positive negative 1 and positive negative 2. And q must belong to the set of elements consisting of what? The coefficient of 1 here, which would simply be positive and negative 1. So let's hold q fixed again. Let's call it at 1. And now let's check for the values for p. If p is, let's take positive 1, then we have 1 squared, which is 1 minus 2, and that certainly is not 0. If p is negative 1, then we'll have negative 1 squared, which is 1 minus 2, which is not 0. Let's try the other one. If p is 2, we have 2 squared, which is 4 minus 2, and that's not 0. If p is negative 2, we'll have negative 2 squared, which is 4 minus 2 is still not 0. We've checked that for q is 1. Check it for q is negative 1, and I think you'll end up with exactly the same thing. Therefore, what's your conclusion about the equation x squared minus 2 equals 0? Brenda? There are no rational roots. Therefore, x squared minus 2 equals 0 has no rational roots. But if they have no rational roots, well, but let's look at x squared minus 2 equals 0, and let's write it as x plus root 2 times an x minus root 2 is equal to 0. Therefore, x is negative root 2, or x is positive root 2, and I think you'll agree that our solution set is negative root 2, comma, positive root 2. Now what then is our conclusion? Here we found two numbers which are roots of the original equation, and our theorem tells us that there are no rational roots. So therefore, what's our conclusion about these two numbers? What can we say, Tim?
They're irrational.
Therefore, negative root 2 and root 2 are irrational numbers, okay? And here's a nice little way in which we can show that a number such as root 2 is not rational, and indeed is irrational. Let me give you your homework assignment for next time. This will be assignment number